So this video is going to focus on the practice problems related to resonance structures. If you haven't already done so, I'd recommend watching the lecture video on this topic first, and then going over to do those practice problems. And once you're done with those, you can use this video to double check your answers. So for this first question, our goal is to draw in arrows that show the movement of electrons between the given resonance structures. And so we can see that the area that is different between the two structures is that highlighted in blue. And so to start off this question, what we would first want to do is draw in the lone pair of electrons on that oxygen. And so on the left, we would have 2 lone pairs, and then on the right, we would have 3 lone pairs that in each of those corresponds to the correct charge on each oxygen. And so from here, we can see that what happened was that one of the pairs of electrons in a bond moved up to the oxygen. And so to show that, we're going to start our arrow at the double bond and end it at the oxygen to show that the electrons were initially in that bond and now they're on the oxygen. All right, for this next one, I can similarly highlight the atoms that are within the conjugated system. And so on the left right here, we can see that that positive charge indicates that there are no electrons at that carbon. And then we also have a double bond. So we have a pair of electrons that was on this right side of the molecule that is now in the middle 2 carbons. And so to show that movement, we would start again with where the electron started and move the arrow or end the arrow where they ended up, which is in this double bond here. I can highlight those to help illustrate that. All right, in these next ones, we have 3 sets. So again, we can start off with drawing in lone pairs. And so I really recommend drawing in lone pairs whenever you're working with heteroatoms. It's a little bit trickier to do it with carbons, so it's not really worth doing it then. But with heteroatoms, I really recommend drawing them in because it helps show where electrons started and ended up. So here, let's start off with this oxygen. And so whenever oxygen has a negative charge, it usually has 3 lone pairs. And then a neutral oxygen has 2 bonds and 2 lone pairs. So I'm just adding those into all the oxygens here. And then on the right side, we also have a oxygen that has a negative charge. And so here I'm going to add in those 3 lone pairs. And so let's start with first going from this structure to this structure. And so here we can see that this oxygen up here started off with 3 lone pairs and ended up with 2. And so that to us indicates that we had one of these lone pairs leave the oxygen and form this double bond, which we can see is in that middle structure too. And then we can't stop there because then this carbon right here that I highlighted in purple would end up with 5 total bonds if we just did that first arrow. And so since carbon can't have 5 total bonds, we have to do one more arrow push to move this pair of electrons from this double bond up to that carbon in the middle. And so that also aligns with having this lone pair of electrons that corresponds to where those were in the first place. So let me color code this just to help illustrate this. We have this double bond right here ends up as those electrons there. And then this green highlighted electron pair ends up in this double bond right here. All right, so now let's go from this middle structure to this one on the right. So from here, we can see that this lone pair on the carbon disappeared, and we ended up with an extra electron pair on the oxygen over here. So to illustrate that, we would also have 2 arrows. We would move those electrons down to form that double bond. And then we need to move one of these double bond oxygen pairs to the oxygen. And so I can similarly highlight that here. So this electron pair is also orange, ends up in that double bond. And then I can do let's do a red to help differentiate. We have this lone pair was this double bond right here. All right, let's do this next one. So here we also have 3 different states. So let's start off with first going from this structure to this structure. And so here we can see that we have the nitrogen. Let's first draw on those nitrogen lone pairs. So we have one lone pair right here in the nitrogen. Each of the oxygens in the neutral state has 2. And then in this last one, those pairs are already drawn in. We can see we have 3. And so our first step is going to be to bring down these nitrogen lone pair of electrons. And again, we're always starting the arrow at the electron pair and then drawing it to where those electrons end up. So this electron pair that I just highlighted in red ended up right here. And so we can see that that red arrow corresponds to those electrons jumping down and forming that double bond. Then from here, we can't stop with just that one arrow because then this carbon right here that I just drew a big arrow to, that one would end up with having 5 bonds if we stop there. So we have to move up this double bond to this carbon right here. And that lines up with where this lone pair ends up. Let's do a different color for that. So we have this green electron pair used to be this green double bond. So we're done with that one. So we can do this one to this state now. And so from here, we can show that this electron pair jumps down to form that double bond and then bumps up electrons to the oxygen. All right. Okay, so let's move on to this next question, which is for each of the following structures, identify the atoms that can participate in resonance. And so for this one, what we're looking for is an extended conjugated system. So here we can see, and again, similar to what we talked about in the lecture video, we're looking for double bonds or electron pairs that are separated or are within a conjugated system. And so here we can see that all 3 of these, or all 3 of these double bonds that I just highlighted in green, are part of one system that can participate in resonance. And here, this double bond cannot participate because it's separated from the rest of the system by an sp3 hybridized carbon. And instead of saying sp3, I'm going to say a carbon with 4 sigma bonds, because this carbon right here has 4 sigma bonds. So there's no way that this carbon right here can ever participate in any sort of resonance. So this double bond is not going to be part of that green system. All right, let's move on to the next one. So in this one, we actually have 2 separate systems. We have this ring system right here, where those are conjugated double bonds. And then we also have this amide right here, where the lone pair on this nitrogen we could draw in a resonance structure with that carbonyl. And we have a practice problem later on in this worksheet that goes through how to do that. All right. In this next one, we have a carbocation. And so we know that a carbon with a positive charge has an empty or can accept electrons. And so we next want to check, are there electrons that are close enough to that positive charge to be able to participate in resonance? And so we can see that we have these double bonds that are 1 away. And so we end up having that this highlighted green system is a part of, or they're all connected. In this next one, we have a negative charge on this oxygen, or a positive charge. And so similar to the previous ones, we can, all of those atoms can participate in the resonance system. And again, a very key part of this is that we are excluding this carbon and this carbon because they're both bonded to 4 bonds here. Similar to that first one that we did. One thing I really recommend is that if you're not really sure, what I would recommend is drawing in those hydrogens. So when you draw in those hydrogens, sometimes it becomes a lot more clear that that carbon already has 4 bonds and cannot participate. All right. All right, so let's get into the kind of more tricky one. So these are going to be drawing in all the possible resonance structures and then drawing the resonance hybrid. And so we can start off with that one from the previous question. And in that previous question, we already identified that these are the only atoms that can participate in the resonance. So here, what we can do is draw. We know that we always want to start with an electron pair and place it in a new location. So we don't have any electrons in this top carbon right now. And so we want to think about how can we move electrons to that site. And so here we have a double bond. So we could show the movement of that double bond to a new position right here. And then as a result of that movement, we end up with a positive charge on this carbon on the bottom left, because that carbon now only has 6 electrons. So to help illustrate this, I'm going to draw in all the hydrogens on this molecule. And so after that movement, we can see that that bottom left carbon in purple, that one only has 3 bonds because it doesn't have like the either 4 bonds or I guess doesn't have 4 bonds. All right, so then from here, we want to draw on the next resonance structure, which is going to be the movement of this bond right here. And so we can show this bond jumping over to form that bond here. Oops, that was a bit messy. And then similar to that previous question, we actually end up with a positive charge on that carbon now. And if you're not sure why there's a positive charge, I would recommend drawing in those hydrogens and keeping track of all of them and just double checking to make sure that that lines up with what you're thinking. All right, we can next keep on circling those charges around. So we could also draw in this next bond right here. And then same thing with this last one. We end up having this one right here. And positive charge on that bottom carbon right there. And that should be all of them. I think it's pretty easy to accidentally do one less than you actually have. So just double check that in your answers you have all of these structures. All right, and so to draw out the resonance hybrid, we want to take the base structure of all the sigma bonds, which is just going to be that ring in that methyl group. And then what we want to do is show dotted lines across the entire system where those double bonds can participate in. And so we're using those dotted lines all throughout the center of that entire ring. And then next we would want to place delta positives on every carbon that ended up having a positive charge in this system. And we actually end up having delta positive on every carbon within this ring just because of the ring system. It's not that common where you end up having a positive on every single carbon within a conjugated system. It just happens to be the case up here because we have a like a circular system. All right, so I will actually see this in this next one. So here we have just these here. And so here we can show the movement of the first bond over here. Then we can show that next jump over. And now in this final structure, we've reached the end of our conjugated system because we're separated, where this purple carbon right here interrupts the structures that we can draw. So we can't move this double bond on the end over because we have this sp3 hybridized carbon that's breaking up the system. And so from here, we're done with our entire system. And we can draw in our resonance hybrid. Which is going to be the initial structure of what we had. And then we're going to take dotted lines across the entire conjugated part of the system. And so here we can see that it's those 5 carbons that are in the middle. And then we're going to place delta positives on just the carbons that had a positive charge in any of those resonance structures. So we had a positive charge here, and a positive charge here. And that's like what matches up with the delta positives in the resonance hybrid. All right, let's move on to the next one. So here we have an amide. And so we can show first the movement of these electrons up. And so whenever you see a carbonyl or a carbon double bonded to an oxygen, this arrow right here is the first one that you should be thinking of doing. And so this would be a plausible resonance structure here, where we move an electron pair from the double bond to the oxygen. And then we end up with a positive charge on that carbon. And so in this structure, we can actually go one step further, and we can have that this electron pair on the nitrogen can come down to form a double bond. And so since we had electrons leaving that nitrogen, it ends up with a positive charge. And something that I recommend is that if you're not sure how to keep track of charges, I recommend going back to that skeletal structures with charged molecules and kind of going through and making sure that you're comfortable with identifying how many lone pairs something has and how to draw any charge based off the number of bonds and lone pairs that an atom has. All right, and so here, this is our final structure. And so we can draw in the resonance hybrid. And so our resonance hybrid is just going to be that base structure. And then we can show dotted lines throughout that entire system where we transferred electrons, which is just between the nitrogen, carbon, and oxygen. And then here we're going to have multiple charges because that oxygen had a delta and minus at some point. Then this carbon right here had a delta or a positive charge on one of the structures, so we'll put a delta positive. And then that nitrogen also had a partial positive charge because it had a positive charge in this last structure that we drew out. All right, this next one, so a common question that I get is, how do you know where to start a resonance structure when you kind of look at something like this and there isn't kind of like an obvious functional group to start with? And so here we can see that we have a positive charge on an oxygen. And so whenever I see a positive charge, I think about what electrons could move up to help fill in that positive space. And so here we can see we have a double bond that's adjacent there. And so our first step can be bumping up those electrons to the oxygen. And so we can draw in our structure here. Oops, we don't want a double bond there. And so now this oxygen has two lone pairs and two bonds, so it's going to be neutral. And instead, we're going to end up with a partial or a positive charge on that next door carbon, because this carbon no longer has four bonds. It now has only three. And again, to keep track of this, we could draw in those hydrogens at the beginning to help keep track of that. All right, from here, the next thing we can do is show this double bond moving over here. And we would get our final structure right here, where we end up with a positive charge on this top carbon. And again, a really key part to this is that we cannot keep going. This carbon right here and this carbon right here that I highlighted in green, both have four bonds, four sigma bonds already, and so they cannot participate in resonance. All right, so let's draw out the resonance hybrid for this one. So for this one, we're going to redraw the base structure. And then we're going to do dotted lines across all the regions where we moved electrons. And then from here, we're going to put a delta positive on all the atoms that had a positive charge within any of the structures. All right, last one here. So here we can draw in those lone pairs to help guide what we want to do. And so here we have a negative charge. And so a negative charge, whenever we see a negative charge within a resonance structure, a place to start would be to start with those lone pairs of electrons. And so we can start with this lone pair of electrons and move it down here. But then if we stop here, the problem is going to be is that we would form this structure right here. And so a problem with this is that this carbon right here now has five bonds because it has those two double bonds and then a single bond. So we cannot form this. And so if we move those electrons down on the left, we have to do something about that double bond. And so the way to, or what we could draw is show those electrons moving up to this carbon right here. And so our final structure for this one would end up looking something like this, where that lone pair is now on that carbon instead of the oxygen. And we instead have a double bond between the carbon and the oxygen. All right, and then from here, we can show the movement of those electrons coming down and then bumping up those electrons to the oxygen. And then our final structure would end up looking pretty similar to the one that we started with, except that charge is now on the top oxygen instead of the bottom one. And then to draw the resonance hybrid, we would redraw our entire structure and then place the corresponding negative charges where we saw a negative charge within any of the individual structures.